Hi, and welcome to my Neutrinos from Home talk. My name is Kevin Kelly, assistant professor at Texas A&M University here in College Station. I'm going to talk about how we can use neutrino facilities as machines to search for new physics in the form of long-lived particles. Often when we think about neutrino detectors, we have a whole swath of experiments and environments in mind where we can search for novel signatures of neutrinos interacting in detectors, oscillation physics, and other classes of beyond the standard model physics. Broadly speaking, we can lump these detectors into two categories, those made of liquid, like the liquid argon time projection chambers at SBND and Icarus microboon, or other liquid detectors. We can also think about detectors that have comparable volumes to these liquid ones, but much smaller masses that are in the form of gaseous detectors. For instance, the proposed near detector for Dune consisting of a gaseous argon TPC falls into this second category. Now, the first category is excellent for looking for signatures of new physics that are rare events determined by particles scattering in a detector. But this second class is going to be highly advantageous looking for new physics manifesting itself in the form of a new particle decaying in a detector volume. That's because any sort of background associated with neutrino scattering in this environment is going to scale like the mass of the detector, whereas these signals will scale like the volume of the detector. And so we'll pick up a relative factor of densities of these objects when looking at new physics in these gaseous argon detectors. So what do I mean as talking about neutrinos as a long-lived particle facility? Well, I mean this in three steps, broadly speaking. In general, neutrino facilities today are sourced by high-intensity beams, mostly proton beams, hitting targets to produce, in the end, a downstream flux of neutrinos or antineutrinos that are then studied as they interact with the detector. We have a proton beam, for instance, here hitting a target, producing many standard model mesons, like pi pluses, pi naughts, k minuses, and etas. And those are mostly moving in the forward direction due to kinematics. The magnetic focusing horns tend to focus mesons of one charge in the forward direction to focus positively charged mesons to produce a neutrino beam, or negatively charged mesons to produce an antineutrino beam, or vice versa. However, if we have new physics at play, for instance, if we have new physics like a dark photon that can be produced in the decay of a neutral standard model pi naught, or a heavy neutral lepton that can be produced in heavier, say, charged kaon decays, then those particles can be produced in this 50 to hundreds of meter decay volume. And some fraction of those new long-lived particles will be produced in the forward direction and can in principle be detected at our neutrino facilities. However, in most of these models, like dark photon, heavy neutral lepton models and the like, these particles will be metastable. And so they won't be infinitely long-lived, and some of them could decay, producing a very striking signature in the neutrino facility. So in these three simple steps, not only can we study neutrino events scattering in our neutrino detectors, but we can also look for the evidence of new long-lived particles produced in this beam. So as a case study, let me understand how we can look for heavy neutral leptons in a scenario like this. So heavy neutral leptons are an extension of the standard model, where we assume that we have some new light fermion that has some mass M4 and some mixing to the standard model flavor, for instance, in this case, to electron flavor that we call UE4 squared. What I'm showing here is a set of experimental constraints on this hypothesis that spans a very wide range of magnitudes, all the way down from the electron volt scale masses up and beyond the TeV scale. A number of constraints, for instance, from oscillation experiments, populate this constraint plot at low masses and colliders at high masses. If instead I consider coupling to muon flavor, these constraints get a little bit weaker, but there's still a number of ways to look for these types of heavy neutral leptons. And if instead I look for heavy neutral leptons coupled to tau flavor, the constraints get considerably weaker due to the challenges associated with studying charged tau leptons. Let me go back to this muon coupled scenario and zoom in a little bit on this, say, MeV to 10 GeV window. This is a very currently active region of study. For instance, T2K and microboon have set some of the most stringent limits in this parameter space in recent years. I've just linked to a few of those recent studies here. But if we look here, we see a lot of experiments that may be familiar to neutrino physicists, names like Super Kamiokanda, T2K, microboon, and the like. These experiments are all looking for heavy neutral leptons in a manner as what I discussed above, where you produce these new things in a beam and allow them to decay in some active volume. So as a concrete example, let me consider the upcoming DUNE experiment at Fermilab. What we did here was we simulated the production of standard model mesons according to the DUNE infrastructure. And we asked how well we could get these particles to decay into heavy neutral leptons that are pointing in the direction of the DUNE near detector site in a span of 5 years. So something like 5 times 10 to the 21 protons on target total displayed here. What you see is that depending on the mass of the heavy neutral lepton, the dominant contribution of these things is going to be from whatever meson can produce it that is produced most copiously in the DUNE environment. So pions, kaons, and d mesons, and the like. Once these particles are made, you want to ask, okay, if they're pointing in the right direction, what's the likelihood that they decay inside my detector and leave one of these striking signatures? Well, these heavy neutral leptons can decay in a wide variety of signal channels, many of which would be very interesting for an experiment like DUNE to study. And so here just shows a subset of this result where I've assumed that the heavy neutral lepton couples only to muon flavor. And I've divided my signal class into various signal channels, the heavy neutral lepton decaying into a neutrino and an E plus E minus pair, or a muon electron pair, or decaying fully visibly into a charged muon and charged pion, or charged muon and rho meson. And what we see here is that in comparison with other existing constraints in gray and black, DUNE can extend on these existing constraints by, in some cases, orders of magnitude by looking for these various final states. So in general, there's tons of parameter space for a potential discovery in DUNE. And you can perform more complicated searches for combinations of mixing if you so like to extend the reach. I'll point to some existing work predating our study and following it that have shepherded some of these analyses into more sophisticated versions. I'm very excited to see what DUNE will offer in this regard. Just to place this in larger context, we have looked at electron flavor coupling and tau flavor coupling as well. And again, we see that there's some very impressive capabilities with DUNE's near detector constructed of gaseous argon. Now, I'm optimistic, I'm hopeful for the future, and I want to understand what we would do with a heavy neutral lepton discovery. And the most natural thing that I would do is try to determine whether there is lepton number violation in this neutrino beam. Whether or not there's lepton number violation in this system is an equivalent question to whether or not this new particle is a Dirac or a Majorana fermion. Equivalently, whether this new particle is or is not its own antiparticle. And because this new particle is mixing with the standard model neutrinos, then it would directly be related to whether or not the standard model neutrinos are Dirac or Majorana fermions themselves. The simple framework in which you would try to perform this study is you imagine you have a perfectly pure heavy neutral lepton source, like positively charged kaons decaying into positively charged muons and this HNl. You then look at the decays of this HNl, and you see whether it decays into a mu minus and a pi plus, or a mu plus and a pi minus. Now, if this object is a Majorana fermion, and there is lepton number violation present in this system, then these two chains will happen with equal probability. However, if this new particle is a Dirac fermion, then only the top process can happen by lepton number conservation. So we want to address whether these two are happening with equal probability. However, there are two natural challenges that come here. One is that there's no such thing as a perfect heavy neutrino source. In a beam environment like DUNE, you'll have K plus production as well as K minus production. And so you will muddy the waters and have some objects that have different lepton number purity in the source. The second challenge is that there's no such thing as a perfect detector. No detector can 100% of the time tell the difference between a mu minus pi plus final state and a mu plus pi minus final state. Nevertheless, we still think that DUNE can do some analyses in this arena For instance, what we show here zoomed in on the parameter space previously, the purple line demonstrates where we think Dune has sensitivity to discover a heavy neutral lepton in one of these final states and decaying to a muon and a pion. But these black lines indicate regions of parameter space where additionally Dune will be able to separate the Dirac and Majorana hypotheses of this nature of these new heavy neutral leptons at the 3 sigma level. They'll be able to do this even if we have an imperfect detector that can only identify final states correctly 75% of the time, shown by the black lines. Now, let me pivot and talk about a different context of beyond the standard model particle production in a facility like the Dune beam or other proton beam dumps, and that comes from electromagnetic showers. And I'll point to this software that my collaborators and I put out just a couple of months ago called Petite, the package for electromagnetic transitions in thick targeted environments that's fully available on GitHub. Petite aims at understanding how electromagnetic showers develop in the standard model in proton beam dump or other beam dump environments, and how we can use those simulations to understand the potential for BSM production. So in the standard model, if I inject, say, a photon into some thick material like steel, that photon will convert into a pair of an electron and a positron. Those particles will continue propagating through this thick target, performing processes like electron bremsstrahlung of photons, photon pair production off nuclei, and positron annihilation into photon pairs. What's been identified in the literature in the last about 6 years is that these can also be excellent sources of beyond the standard model production from secondary electrons, either in an electron beam dump facility or a proton beam dump facility. So for processes involving, for instance, a dark photon, we can have annihilation of positrons off electrons into dark photons, or bremsstrahlung of these objects off nuclei. And in this paper from the Celentano group, it was shown that in certain facilities, these production modes can actually dominate over previously considered ones in proton beam dump facilities. Now, the challenge with understanding this type of beyond the standard model production in an environment like this is that often we're interested not in facilities where we can really pick apart a shower like this, but we're interested in the production of new particles in the far forward direction. So we're looking in the far forward direction at relatively small solid angle detectors. So Petite is designed to properly treat kinematics of this type of beyond the standard model shower production, simulating the standard model and repurposing it for that type of careful kinematics production. One process in which this is a particularly challenging problem is standard model versus beyond the standard model bremsstrahlung of new vectors off of electrons. In the standard model, because the photon is massless, this photon will often carry away a small amount of energy from the incident electron or positron, and will be pointing in the forward direction. It will have a soft collinear enhancement to that cross-section. However, if the new particle that's being emitted is a vector boson, say with a mass of 30 MeV, it's a significantly higher mass than that of the electron. Instead, this vector boson will actually carry away a significant fraction of the incoming electron's energy and tend to be produced at off-axis angles. To wit, the kinematics of this outgoing vector are significantly different than that of the standard model photon. And so it's not obvious how to repurpose fluxes of photons in a standard model shower to represent that of vector bosons. And so we performed studies of this type of remapping versus resampling approach, coming to our main results in Petite shown in this center panel here, showing that in an electron beam dump experiment, for instance, like that sources the BDX experiment, the kinematic distributions of these vector bosons can be extremely different than both the standard model distribution of photons, as well as well-informed reweighting of those standard model photon distributions. The best way to do this is from the source, and we highly advocate for using Petite to simulate these types of samples. We also calculated downstream production of these new vector bosons using Petite, comparing against some results in the literature. And for instance, we found dramatic differences between our results and previous ones in the literature using Petite carefully, for instance, tracking the opening angles and the multiple Coulomb scattering of particles as they travel through a thick graphite target, as would be relevant for Dune. So to wrap up, these neutrino facilities may indeed be awash in fluxes of new particles. These particles could be long-lived particles that could be performing very interesting new signal channels in our detectors, and we could look for decays of these things in neutrino facilities' active volumes. However, new tools are necessary to better understand how these particles are produced, the rates at which we could possibly detect them in the future. And PETIT is designed with an emphasis on user-friendliness for understanding these scenarios. Finally, I really believe that we should be cognizant of the capabilities of our detectors now in the event that we have a discovery in the coming decade. We want to be planning for those future discoveries now in case we find new physics so that we are prepared. Thank you very much.